Thank you. So, tēnā koutou hoa mā, my name is Matthew, and yeah, I'm a software engineer, and by night I chase auroras. And my talk tonight is basically about magic. So hopefully you'll learn something about seeing aurora tonight. Oh, that's right, there's a clicker. I'm at. Oh, hold on. So what I plan on covering tonight, first we'll be discussing what an aurora actually is. Turns out the sun actually has a lot to do with this, so I'll be telling you how that works. And finally, what you'll probably be most interested in hearing about, how we can see the aurora for ourselves. So to understand how we can see the aurora, we first need to know what they are and how they're made. The sun, this guy, is big, really big. Exactly how big? Well, this guy here, if my laser pointer works. Really? Okay. Anyway, you can see it there, that's Earth. That's Earth to scale with the sun. So you can see just how big that thing is. Now, this is a bar magnet. You might remember using iron filings at school to see its magnetic field. This is a field diagram of what a magnetic field of a bar magnet looks like. Fairly simple. Now, the sun also has a magnetic field, and it's incredibly powerful. Has some key differences though. It's complex and pretty much changes all the time. It's a cosmic energetic spaghetti. It's tangled and oftentimes parts of it get unstable. So this is a magnetic field model of the sun taken about a week ago. As well as sunlight, the sun is constantly bathing the solar system in charged particles traveling at high speeds, known as the solar wind. And the solar wind is itself magnetic and is a major component of what we know as space weather. Because the solar wind is magnetic, it causes disturbances in Earth's protective shield, known as our magnetosphere. And when this happens, the gases in the upper atmosphere emit light, which is the aurora. And our magnetosphere protects us from the worst effects of space weather. If we didn't have a magnetosphere, we'd look like this guy. That's exactly what happened. This is Mars, sometime about 4 billion years ago, lost its magnetic field. The solar wind stripped its atmosphere off, and now it's devoid of all life. The diagram, this one, which I'd unfortunately point to if I could actually laser point to work, shows us basically how. Hold on, I just turned the pointer off. That there is a solar wind, and it's been directed along the magnetic field lines of the magnetosphere. So normally it would get bounced around us. However, when the sun is emitting lots of solar wind, then sometimes it actually gets trapped inside our magnetosphere. So when the solar wind pushes against the magnetosphere on the daytime side, the field lines get pushed inwards until they snap, which it's a bit like a rubber band. And you'll see here that the field lines are actually being, as the magnetotail is being pushed outwards, the magnetic field lines are actually being pulled inwards. They reconnect. A whole bunch of solar plasma that was trapped is then whizzed to the magnetic poles at usually about 10,000 kilometers a second. That solar wind then interacts with the upper atmosphere and produces the northern and southern lights. Every aurora you see is different, and it really depends on what gas molecules get hit by charged particles. How does this work? Well, when a charged particle hits a gas molecule, the molecule itself becomes excited and an electron jumps to a higher energy level. When that electron finally comes back down from its excited state, the molecule returns to what's known as a ground state. But what happens there is the gas molecule actually releases a photon. And that is the light that we see. Different gas molecules actually emit different photons with different frequencies, so that's where the different colors come from. And this process is known as fluorescence, which you'll be surprised to know is actually how fluorescent tubes work. So I was lucky enough to witness a pretty spectacular aurora back in November 2021. This is a photo of it here, and you can see it's made of different components. So the green in the arc at the bottom is emitted by atomic oxygen, and that's about 100 kilometers to 240 kilometers above the ground. So way up. That's basically space, but there's still actually gas up there. During intense solar storms, which this one actually was, you can sometimes see purple emitted by molecular nitrogen. That's actually fairly close to the ground, so that's below about 100 kilometers above, above ground level. Sometimes far closer, depending on how strong the activity is. You'll notice at the top of the curtains there's actually some blue. Now that blue is caused by an interesting effect where the electrons in the solar wind actually get whisked up to the top of the aurora by really powerful magnetic fields. And what's happening here is this molecular nitrogen is actually scattering sunlight. So 100, 200 kilometers up, basically you can see the sun from up there. So the molecules scatter the sunlight and make sort of a bright blue kind of indigo sort of color. Now, a common misconception about aurora is that it's only visible from the polar regions. You'll probably have better chance if you go somewhere like Reykjavik or Tromsø in Norway if you want to see the aurora. However, what actually matters is how close you are to the Earth's magnetic poles. So, this is a map. This shows us where the Earth's magnetic poles are. You'll notice at the top of the map is the magnetic North Pole. That's about 85 degrees north latitude. So that's closest to the North Pole, the North Geographic Pole, which is about where you'd expect it to be. However, you'll notice something interesting here. The magnetic South Pole is actually nowhere near the geographic South Pole. In fact, it's about 65 degrees south latitude. I measured it earlier, and it's actually 500 kilometers closer to Tasmania than it is to the actual South Pole. So as a result, we're actually pretty well placed here in the Southern Hemisphere to see aurora, just because of our proximity to that pole. So where do we sit relative to other cities? So this kind of illustrates it here. New York is pretty far north, but Christchurch, Ōtautahi, is approximately the same geomagnetic latitude as New York. Dunedin has about the same geomagnetic latitude as Edinburgh, about 53 degrees. And Hobart in Tasmania, it's about, geomagnetically speaking, the same latitude as Toronto in Canada, which geographically, they're actually not that far south. So how does the sun cause aurora? There's a few processes that do this, which I'll go into a little bit of detail on. The first one are prominences, coronal holes, and sunspots. Now, prominence can be seen as a large, bright feature looping up from the sun. It's prominent, hence its name. It's a tangled and twisted magnetic field structure which has billions of tons of hot plasma flowing through it, and it's trapped inside it. These can remain stable for a very long time, sometimes several months. I think some have been known to last for over a year, but that's pretty rare. And to give you an idea of just how massive these structures are, see up there? That's Earth. That's a prominence. That thing is huge. So this is a satellite photo of a prominence eruption back in August of 2012. Even though prominences are normally stable, they can still sometimes erupt with pretty spectacular results, as you can see there. So this is a video of that same event. Over a few days, a small group of sunspots developed under the prominence, and the whole sunspot group, they generated a small solar flare. Now, even though that prominence was fairly stable, the solar flare and the energy released from that was enough to actually just, it was kind of like a trigger, and the prominence erupted. So we'll watch it through again. And then, just flicks off into space at very high speeds. The second phenomenon I want to talk about is coronal holes. So unlike prominences where the sun's magnetic field loops back around and connects with the sun again, with coronal holes, the magnetic field's actually unipolar, so the field lines actually extend out into space. What this does is the plasma actually leaks out of the corona. So it's kind of like if you have a balloon and you pop it, and all the air flows out. It's a bit like that with the sun. Plasma leaks out. Coronal holes can persist for several solar rotations. Each solar rotation is about 27 days long, so they can persist for several months. And they're really stable as well, so they don't normally change shape that much, and they certainly don't change location. Because the sun rotates at a constant rate, you can predict them with reasonable accuracy. So if you're looking at trying to figure out if there's going to be an aurora in a month's time, that can be a pretty good way of working out if there will be, or what your chances are. The final phenomenon I want to talk about are the most energetic and exciting of them all, sunspots. So sunspots are actually dark, cooler areas on the surface of the sun. They follow at about an 11-year cycle. So every 11 years, you have the maximum number of sunspots covering the sun, and you have a minimum somewhere in the middle there. So we're actually about 3 years away from our next solar maximum, which should be in about 2024 or 2025. Cool thing about sunspots is they are highly energetic and they have incredibly powerful magnetic fields, and also quite complex magnetic fields. So when they normally release huge amounts of energy in the X-ray spectrum when they do erupt, but that amount of energy being released all at once usually hurls bits of the sun's corona in what's known as a coronal mass ejection. The other interesting thing is they can grow extremely quickly, as I'll show you in the next slide. So this is the sun on 4 different wavelengths. If you look at the bottom right here, 2 sunspot groups are visible. So the one at the top doesn't change all that much. The one at the bottom, however, starts as a single sunspot, and over the course of about 3 days turns into something which is really complex and eventually erupts in actually the largest solar flare of the last solar cycle. So that basically came out of nowhere. And from memory, this one actually produced aurora visible from as far north as Wellington. So it was quite a decent one. Now, the bit you've probably been waiting for, how can we have the best chance of actually seeing aurora for ourselves? So first, a disclaimer. Aurora forecasting is absolutely not an exact science, and I'll probably class it closer to magic than actual science. Even if all the forecasts and data are looking promising, there's a very good chance you're probably not going to see anything, which sounds incredibly depressing, but you do. I've probably done about a dozen or so trips. I normally go out to Birdling's Flat, and of those, I've probably seen aurora about 3 or 4 times. And yeah, so if you actually do see an aurora, with the naked eye, you also probably won't see much color, usually. Sometimes you do actually see color. I've seen pretty bright color myself, but usually it's fairly faint. I've actually colorized the background to be closer to what you're probably going to see with the naked eye for the most part. But you do normally see color. You can see color. It's usually the green stuff, the red and blue and stuff you don't normally see with the naked eye, but you sometimes can. If you do head out, I would highly recommend bringing a tripod and a camera that can do long exposure photos, such as a DSLR. But most smartphones actually these days can do a reasonably good job. Ingredients for success. So for starters, you want some actual solar activity, and you want that solar activity to be aimed at Earth. The plasma cloud resulting from that solar activity, first, A, needs to exist, sometimes it doesn't, and B, needs to arrive nearish our nighttime. You also need an unimpeded view of the southern horizon, and you really probably, for best results, should have dark, moonless skies with no clouds. You can sometimes see aurora or get photos of aurora with a full moon, but that's extremely rare. Usually the full moon completely washes out anything you see. So how do you find out about solar activity? There's a few ways. My favourite way is one website called spaceweatherlive.com. It has a fairly nice and easy to digest dashboard of current solar activity and geomagnetic conditions. There's the Space Weather Prediction Centre, which is an agency in the States that sole job is to forecast these things, because there are other impacts on Earth other than aurora with space weather. And finally, Facebook groups are usually good too. There's other people that are nerds about this sort of stuff that do watch this stuff obsessively and post when there's going to be something exciting in the offing. Now, I'm going to go into a bit of detail about how I made the decision to head out to see the aurora that I did, so I'll cover some of the data and forecasts I looked at, just so you guys get an idea. So assuming you have an event, you want to actually look at the forecast to see when it will arrive. One of the best ways to do it is the WSAN little solar wind prediction model. So this guy here predicts basically when solar wind is going to arrive. which direction it's heading out of the sun from, and sort of how fast the solar wind will be, proton density, all that kind of stuff. There's also the text-based Space Weather Prediction Center 3-day geomagnetic forecast, which is a pretty good indicator as well, just a quick glance of there's probably going to be something. Watching when will arrive. So there's a few tools we can use to watch for the arrival of increased solar wind. One way is Ovation. It's another model that uses live solar wind data from satellites to basically predict the extent of the auroral oval. So basically just predict how far north you can see aurora from. And depending on solar wind speed, it gives between about 30 and 60 minutes of advanced warning. Alternatively, you can also look at the raw satellite data from the satellites ACE and Discover. They've both got, they both measure solar wind and can be quite interesting to look at as well. And when the increased solar wind arrives, it will interact with the magnetosphere and produce what they call a geomagnetic sun disturbance. That is visible on an instrument known as a magnetometer, which is a thing that measures magnetic field. There's a network of these all around the world. There's a few in the Southern Hemisphere, and one of the best ones for this particular area is the one in Hobart. So you can see here, the Discover satellite detected a sharp increase in the solar wind speed about sort of 8:30 that morning. And hopefully you can see it, it's actually a bit dark. And about 70 or 80 minutes later, you can see the trace from the Hobart magnetometer. So it starts off reasonably stable, nothing's really changing all that much, but then suddenly it gets very spiky very quickly. And that's usually an indicator that, yeah, something has hit the magnetosphere and there's probably going to be aurora pretty soon. Ideally, this would happen at night time. This happened during the day. However, interestingly enough, this activity was powerful enough that it actually lasted for another, I think it lasted in total about 18 hours. So we still had decent geomagnetic storming by the time it came to our nighttime. So this is what Ovation was showing when I got home from work that day. And when I saw that, I'm going to say my jaw actually dropped. I was not expecting there to be that much activity that much after the original impact. But basically, if Ovation looks like that, get out there, you're probably going to see something. And the last but most important thing you'll need to know is, will there be any clouds? It seems obvious, but actually in the process of deciding, oh, there's going to be activity, I'm going to head out there, this is actually pretty easy to forget. So ideally, you want real-time cloud coverage imagery. The satellite Himawari 8 provides that, I think, an image every 10 minutes or so. And you can get a pretty good indicator of if there's going to be clear skies. So on this particular night, November 4th, the entire lower South Island was cloud-free. So pretty much anybody below sort of North Canterbury had a pretty good chance of seeing aurora. Now, where to go? The million-dollar question. And the short answer to that is pretty much anywhere with a good view to the south, free from light pollution. Now, the way the South Island is oriented is actually a lot of those places. The entire Canterbury coast, for one. Even North Canterbury, if you've got enough of a view around Banks Peninsula, you've got a pretty good chance of seeing aurora as well. This is an actual map from the Global Aurora Sightings map. And this is places where people have actually reported seeing aurora in the past. So pretty much anywhere along the Canterbury coast, Otago coast down to Southland, and inland as well in some spots. But yeah, the important thing is being able to get above the terrain, so to speak, and so you can actually see the horizon. Now finally, this is a time lapse I took of that night. This was over the course of probably about 2 hours, so this is very sped up. But it was quite a spectacular display. It was definitely something I'll probably remember for the rest of my life. It was really cool to watch and was naked eye visible from the time I went out there, probably from about sunset to when I finally decided to go home at about midnight. And hopefully over the next few years, as we get closer to solar maximum, we'll get to see more of these events. Does anybody have any questions? Yes?
So if you've been chasing auroras for quite some time, is this like the best one you've found, or is this quite frequent?
Easily. So the previous best I saw was probably August 2019, I think it was. And I was able to get some pretty decent photos in camera for the first half an hour, but it died off pretty quickly. This was literally naked eye visible for the entire night. Like I say, didn't have much color. It did have some, but once your eyes adjust to being able to see the night sky, you do see mostly white and sometimes green curtains dancing across the sky. And like I say, it was pretty fantastic. Sometimes I am. I usually watch the other people because the other people know more than I do. But sometimes if there is something that I see, I'll post on there. Then that one Facebook page, which is probably the most popular, is called Aurora Australis New Zealand. So yeah, look that up when you get home. And people usually post cool pictures I've seen as well. And if there's actually activity happening right now, they'll post if there is activity. It's a good question. Turns out quite a few. So one of the most notable, and I suppose Hollywood style, is it plays havoc with the power grid if the geomagnetic storming is large enough. Case in point, in 2001, there was a fairly large geomagnetic storm that actually burnt out a transformer at halfway bush near Dunedin. So that's Transpower now have procedures in place to prevent that sort of thing happening for the most part. But historically speaking, there have been far larger impacts. In 1989 in Quebec, there was a large geomagnetic storm that took power out for like 9 hours to 6 million people in March. So it was kind of cold, so it wasn't really ideal. But other than that, yeah, it can affect GPS navigation, radio reception, that kind of thing. Hello. It really depends. Sometimes activity can come out of nowhere and it's like suddenly you see people posting naked eye aurora in Timaru and it's like, oh my God, I need to get out there. Sometimes it's cool, there's been a massive solar flare and it'll probably reach Earth in about sort of 1.5 to 2 days time. But again, it really depends. Usually sometimes it can be, an hour or so because forecasts aren't perfect and sometimes things happen that people don't quite understand. Sometimes if it's more predictable, then you might get a couple of days' notice. Yes? Oh, that is a very good question. I'd love to. Some point in the future, I would love to go to Iceland, and also Norway as well would be pretty cool. So it'd be really cool if I can see the Northern Lights. But for the time being, I'm pretty happy with the Southern Lights. They are actually not too bad. And I mean, they're not necessarily as spectacular as the Northern Lights, but they can be sometimes. And definitely still well worth seeing. Yes? Because the human eye is actually far more sensitive to green than it is any other color, any other wavelength of light. I think about 1,000 times more sensitive. Not entirely sure why that is, but it tends to be more sensitive. The other thing too is the other colors don't tend to emit nearly as strongly. So yeah, green tends to get emitted fairly strongly and for fairly long periods of time, whereas like in the matter of seconds kind of thing. So each molecule that gets hit kind of lights up for maybe 1 or 2 seconds. In the case of nitrogen and other things that get lit up, it can be in the order of nanoseconds. So the amount of light that actually gets emitted isn't very much. But coupled with the fact that human eyes are very sensitive to green light, means we see green a lot more than any other color. You. That's a very good question, and scientists still haven't worked that one out. So one of the theories is it was hit by a massive asteroid and things happened, but that's basically as much as they know. So that's still been actively researched. Like nobody knows why it lost its magnetosphere. How can you tell? Why do I do it? Because, well, I guess it's magic. Even though you can look at all the geeky science data and satellite imagery and stuff, which all looks fantastic, you still don't know if you're actually going to see anything. And even just driving onto the middle of nowhere, just sitting there watching the stars is enough for me. And then if you can see the aurora on top of that, that really takes the cake. So it's probably a long-winded answer as to why I enjoy doing this. But yeah. Cool.
Thank you.